So hopefully that doesn't fall. So we'll try this. On Friday, we learned about the Net Ionic Equation for a precipitation reaction. I don't think we got this far. Did we? Did I have you do the Net Ionic for the first reaction?
No.
And then we had to stop. Okay. I think I showed it to you, so we'll start with this on Monday.
Yeah. Oh.
I have two on this page. Let's do the first one together, and then I'll ask you to try the second one. So I asked you to grab the solubility rules because we have combinations of ions. Some combinations are soluble, some are insoluble, and therefore would make a precipitate when you mix those things together. So ammonium hydroxide, you've got the ammonium ion and the hydroxide ion. They're really not together because the solutions are split apart. And then we have copper 2 chloride. Those are really split apart. Is there any combination of those ions that would be insoluble and make a precipitate? Ready?
Copper 2 hydroxide.
Yeah, most hydroxides are insoluble. All the transition metals will be insoluble with hydroxide. And the solubility rules will say that unless you have a group 1 or an ammonium compound, hydroxides are probably going to be insoluble. So the Net Ionic Equation would just look like this. You don't have to write the whole equation out. You've got copper 2 ions and hydroxide ions making this precipitate, and you have to write the formula correctly based on the charges, like that. Then go back and balance the Net Ionic Equation. Don't include any ions that are not reacting and changing, precipitating. Yes, sir?
What if you write the whole thing?
That's not the Net Ionic, yeah. Because it says this, this is what I'm looking for. There's a place, I think, for writing the whole thing. When it tells you to write the Net Ionic, you've got to write that. But when you start doing the stoichiometry, I find it a little bit more convenient just to keep it as the whole, what we call the full molecular equation, with everything in it. You'll see, because we're going to get to the stoichiometry today. If you feel like, okay, we got the stoichiometry behind us, I got a pretty good handle on stoichiometry, I'm going to just take a nice big pin and I'm going to stick it in your balloon today. And if you didn't understand that analogy, maybe I'll remind you at the end of the hour what I meant. Try this one. See if you can do this on your own.
Do we have to rate, since that's a solid, you have to rate S?
No. For these, and I'm making my standards what the AP standards are. I personally like the physical states in there.
Right.
The AP, the College Board doesn't require them, so I'm not going to have you do it. It looks naked to me without the physical states, so I really don't like it, but I did physical states for years, and then since the College Board doesn't use them, I thought, well, I'm just not going to hold you to that. Okay, so what's our precipitate in this one? Or is there not one? It's possible that you won't get a precipitate if everything stays soluble. Justin? AgCl, right. And this may have been a tricky one at first because chloride, the solubility rules say, well, chlorides are typically soluble, but there's 3 exceptions. You have to know those 3 exceptions too. Hank?
Wait, it says most when it says like most salts are soluble in citrus salts, ones like Li and NaK, are those the ones that come to precipitate? Or?
No, except for those. It'll say that most are slightly soluble, which really means insoluble.
So Li, NaK, CS, RB.
Those are always soluble in everything they're with.
So do they form to precipitate or?
No, soluble means they stay dissolved.
Okay.
So they're the ones that don't form precipitates. The ones that are slightly in the rules, they do form precipitates. Okay? So, we have silver ion and chloride ion making AgCl. There's our Net Ionic Equation for this reaction. Anything else about this page? Yes, Peter.
Number 1 says most nitrate salts are soluble.
Yes.
And number 3 says most chloride, bromide, and iodide salts are soluble. Notable exceptions are salts containing Ag.
Yeah, like this one. With those ions.
Yeah, but if it says most salts containing silver 1, if those aren't soluble, then what is silver nitrate not be soluble?
No, it's referring to chlorides, bromides, iodides. Those are soluble with almost everything except those three. Silver, mercury, and lead.
That's just talking about those.
Yes, just those. Yep, just the halides. Sorry about that noise. I think maybe it is. Sometimes when we turn the faucet on, it relieves the pressure.
I didn't even realize that.
You didn't even notice there was that?
I didn't.
Oh man, it makes me crazy.
It's been so like normal now.
Okay. Now we're gonna have the sound of dripping water. That's funny that you didn't even notice that. Okay. Anything else about these? And by the way, those chloride, bromide, iodide exceptions, you have to know those three exceptions, silver being one of them. They show up a lot. So that's a good thing to know. I have a memory trick. There's a picture. When I think of a exception for halides, there's a picture I come up with in my head, and it helps me remember every time. I'll tell you that tomorrow. I'm not giving you that today.
Why not?
It's a secret.
No reason.
Is it reading quizzes tomorrow?
No, the reading quiz is about something new. It's about acids and bases. Mark?
Where does it say that chlorine is insoluble?
Rule 3. It says chlorides, bromides, iodides are soluble with everything except for those three.
It's when it's like shortened.
Okay. Okay. All right. Now, this problem, there's two things that I like about it. It is right out of the book. One thing that I like is that it provides us for some stoichiometry to do. And the second thing I like about it, it's got the word aliquot in it. What a great word, aliquot. The word just means a measured sample, but I'm pretty fond of it. Let's go through this one together, and then I have a nasty one for you to try after this one. You hear that?
I hear that.
So we have some stoichiometry that we're going to have to contend with. A asks for a balanced equation for any reaction that occurs. It's possible that this is a no reaction. It's not likely, though. I think there's probably going to be a reaction. Can you identify any combination of ions here that will precipitate?
Yeah.
What's going to precipitate mean? What is it, Freddie?
Iron 2 hydroxide.
Yeah, the iron 2 hydroxide. Again, we just seen it on the previous slide. Hydroxides are generally insoluble with almost everything, except those things that are soluble all the time. So, now it didn't say to write the net ionic, did it? Anthony, this is for you. What? So, we'll write the whole thing. For this case. I have sodium hydroxide, there's NaOH. And then we have, I'll put this on here. And we have iron 2 chloride, FeCl2, which is soluble. That's why it's dissolved right now. And then that makes, we just switch the positive ions to the other thing. Iron goes with the hydroxide, FeOH taken twice. Those are solid. And then we have NaCl. Now, when you're writing the products, if you write NaCl2 because the FeCl had a 2 at the end of it, if you put NaCl2, I'm going to break your hand. Because you are way past getting those formulas wrong. Okay? You write formulas based on balancing charges, not what the subscripts are on the other side of the hand. The equation. If you're hung up, I'll break your hand. You're like, oh my gosh, I'm really not going to break your hand.
So you're not supposed to balance it?
Yeah, you have to balance the charge when you write. Yeah, you have to go back and balance the equation. Just write the formulas correctly first. I'm saying don't write NaCl2 for your other product. Just because when you see the 2 after the Cl there, you think there's got to be a 2 after the Cl there.
2 NaCl?
Yes, yes. So now we have to go back and do that.
Oh.
But that's different from saying NaCl2. You know what I mean?
Okay.
And then we have to have a 2 there. So yeah, I'm not saying don't balance the equation. You have to. We're doing stoichiometry. Okay. That's it for part A. Part B, I don't remember what part B was in the book, and I just left it out because I didn't think it was worth our class time. Part C now, what mass of precipitate forms? Okay, well that's not bad. We can do this. It doesn't give us grams or moles, it gives us volumes and molarities. But if you know volume and molarity, you can find moles, right? From the molarity formula? You can. So let's go ahead and do that. We know that molarity is moles per liter. So we know the molarity of each one, and we know the liters of each one, so we can find mole. Okay, I have 0.1 liters times 0.2 molarity gives me 0.02 moles of that reactant. You catch that? I did change this to liters. Almost every time you're going to be given milliliters for solutions, you've got to change the liters for molarity. The FeCl2, same thing. I've got 0.1 liters and 0.2 molarity, so that makes 0.02 moles on that one. And the question is, what mass of this forms? Well, that's not bad. It's pretty easy. Especially when we're even starting with moles. Now, I'm given the moles of both reactants. Figure out the limiting reagent before you do anything for the product. And by the way, I'll just say this about the course in general. We're still kind of learning the course in general, what is expected for you for the whole year. And I'm going to tell you this, and this one you probably have caught on to already, but it is 100% true. Everything we've already done in the course is fair game for what we're doing currently. Like, we've already done stoichiometry. That doesn't mean we don't do it in this chapter too. Okay? And after this chapter is over, whatever we learn in this chapter, that's fair game for everything else we learn about too. And so on the test, you may be seeing questions that have to do with things that we've done earlier in the year. Sorry, that's going to happen. Okay? So, yeah, everything builds in this class, and you're going to see there's a lot of connectedness of the topics that we do.
Are we going to have organic chemistry again in the new chapters?
Not really. No, I mean, there are going to be organic compounds that we'll see. I'll give you the name of something. You have to figure out what it is in order to do the problem. But there's not a whole lot of like organic reactions that we're going to worry about. Organic is kind of an island. That's why we did it first. We do it, we learn about it, and we kind of move on. But once in a while, organic comes back up. And I'll kind of laugh as you say, oh, organic. But it gives me amusement. when you guys do that. Okay, so now having said all that, do you have the mass of the precipitate? Which one is the limiting reagent? Yeah, there should be a 2 to 1 ratio here. Do I have twice as many moles of Na as Cl2? No, FeCl2. I've got the same number. So this one is my limiting. And therefore, that's what I use to determine how many moles of iron hydroxide I get. So it's this, 0.200 moles. Geez, it's so easy we don't have to, except until we get to the conversion part, NaOH. Times 1 mole of iron hydroxide and 2 moles of NaOH. That convert to grams, 80 something, isn't it? 34. Right? Okay, so the math is nice because we have 0.2 divided by 2. Sorry, this is 0.02 divided by 2, which is 0.01. And then times that number. So it's just 1/100th times that. 0.898 grams. Yes? That's our mass of the precipitate. Then we get to the last question. The last question is calculate the concentration of each ion remaining in the solution after the reaction. How many ions of the 4? There are 4 ions here. There were 2 ions in sodium hydroxide. There were 2 ions in iron 2 chloride. So we got 4 ions that we're dealing with. How many still remain in the solution, not precipitated? How many?
2.
No.
4.
No.
3.
1.
3 is correct. We started with 4 ions. One of them is not present in the solution. I mean, it's there, but it's not in solution dissolved. Which ion is not any longer dissolved in solution? It's the hydroxide ion. Why? Yes, because it made the precipitate, and it was the ion that ran out. So all the hydroxide ions are now precipitated out, not dissolved. What about the iron? That precipitated too, but it was the excess reactant. So there's some iron that got precipitated, some is still in solution. You with me on this?
Wait,
Yes, Anthony?
why did the OH run out?
Because it was the limiting reactant.
What happened to the NA?
Na never got used.
Oh,
The amount of
yeah.
Na that was
Oh.
there is still kind of hanging around, not doing anything. It's an excess ion. It's not excess. It's a spectator. So that just stays there.
Wait, it's just like that.
So we're going to have to give 3 answers for part D. We have to work it all up. Karthik, got a question?
How did you know that NA, like, nothing happened? Like,
Because it's a spectator ion. You just have to know. And if we write the balanced net ionic equation, it would be iron ions plus hydroxide ions make this. The sodium doesn't do anything in the reaction. Because Na was aqueous at the beginning, and Na over here is aqueous at the end. So it didn't change. The hydroxide changed because it was aqueous over here, but it's a solid over here. So that had a change that it made. And these questions you have, they're great because as we begin and we kind of walk through this, as you see a couple of examples, it'll all start to come together and you'll see it. But at first, it's not obvious. So let's go ahead and do this part. Let's do the sodium first. The sodium really is not too bad. Remember, it's the moles divided by liters. That's how we get concentration. I'm using this symbol. You remember this from last year from Chem 1? The brackets around a symbol represent molarity. Oh, thank you.
Yeah, no problem.
Abhishek. Got it. Thanks. So the sodium concentration at the end is probably not going to be what you think it is. It's moles per liter. How many moles of sodium did we start with? Right. 0.02 moles of sodium. And what was the volume there of... Now, we're looking for the final concentration of sodium ion. We have 0.02 moles that didn't react, so the moles are the same. What is the volume that I put in the denominator?
0.4.
0.1.
It's not 0.4. All right, it's not 0.1. It is 0.2. Somebody's saying 0.2. That's correct. Why? Because we have 100 ml of one solution put together with 100 ml of the other solution. The volumes will be additive. And usually, in the book problems, they'll say, assume the volumes are additive. So I want you to remember, anytime you mix solutions together, everything becomes more dilute. The volume goes up. And remember that. So anytime it asks you for the concentration of something at the end, one of the things you want to look at is, okay, did I combine two solutions? Because the volume is going to be increased. So the sodium no longer is 0.2 molarity because it got diluted. That's our volume. We had 100 ml plus 100 ml, so that makes a 200 milliliter final volume. Venkatesh?
When a precipitate forms, does the volume change when something is made?
No, we assume that it doesn't. Does it change on a very minuscule level? Yes, but it's not measurable, practically measurable, so we just assume that they add together to get the same value. But in reality, yes, it does change. Okay, so do we see how to find the new volume, or the new concentration of sodium? Yes. That divided by that is what? 0.1. So sodium started as 0.2 molarity, but then it got diluted to double the volume, so its concentration got cut in half. Okay, now the next one for us to do, let's do the chloride ion next. Moles divided by liters. How many moles of chloride did I have? 0.04 moles is right. 0.04. Because every FeCl2 has two Cl's in it. Yeah? So if I have 0.02 moles of FeCl2, there are 2 times that many moles of iron. When that thing dissolves, all of the chlorides break apart from each other. So it's 0.04 moles over what volume? The 0.2. The volume is going to be the same for all these because they're all still in the same container, same solution. So 0.04 divided by 0.2 is going to be 0.2. We good? All right, then I saved the best for last. The iron concentration. We need to know how many moles of iron still remain. Some of it precipitated out, but some of it still remains in the solution. Okay, so how much iron? We started with 0.02 moles. I'm going to go ahead and write that. The concentration of iron at the end is 0.02 moles minus the amount that reacted. How much reacted?
0.01 moles.
Yeah. How'd you get that?
By dividing the excess or limiting divide or converting it to moles of that.
Right. All of that got used up. All 0.02 moles got used up. Now, there were 0.04 moles of chloride ion. We already had that over. It's not the chloride. I'm looking at the wrong thing. It's sodium and chloride. This is my precipitate. Sorry. We had 0.02 moles of hydroxide. And we needed 2 hydroxides. Notice the formula is FeOH taken twice. So every one of these ions needed 2 hydroxides. So we only used half the amount of iron as we did hydroxide moles. So the amount used was 0.01 moles of iron. So that remaining numerator there is the amount of iron that didn't precipitate. And then divided by 0.2 liters. Yes? Just go through that again. These two things react in a 1-to-2 ratio. So when I use all this up, because I need 2 of these for every one of these, I'm only using half of that up, which is 0.01. That's where I got that from. Now I will tell you this also. In the solution guide and in the book, the authors will suggest that you do everything with the Net Ionic Equation. I find that a little bit more confusing than doing it with the full molecular. So when I'm doing the stoichiometry, I prefer to have it this way. But be warned that when you look at the solution guide, it's just going to give you the Net Ionic. You can do it with the Net Ionic, and it's fine. It just, I don't know, this is just more at home, I guess, because that's the way we've always been doing stoichiometry. Justin?
Why did you take half of CL?
Because the CLs never reacted.
Oh, so they're still
They're spectators, so I had 0.04 moles of the CL to start with, and since they're a spectator, they did nothing. That's why I ended with 0.04. But the iron is a different story. Some of the iron got used up and is gone now. Half of the moles of that, because of the 2-to-1 ratio. See the difference? When you have a spectator, the amount you started with is just what you have at the end. Okay, so 0.02 minus 0.01 is 0.01 divided by 0.2, which is 0.05 molarity. It's 10:04. Any other questions about this one? I'd like to have you take a look at one more. It's going to take us the rest of the hour. Yes?
Why are we calculating everything?
Oh, because all the OH is gone. It was the limiting reactant, and so all 0.02 moles of it have made precipitate. So there's no hydroxide left in the solution. It's in the container still, but it's not. When they say in solution, it means dissolved, and there's no hydroxide still dissolved. All right, somebody was about to ask a question. No, we're good. Go ahead.
In the reading book, we're learning about the concentration of the ions. Then we have to also multiply the moles by the exponent in the solution. I remember something like that.
You mean the coefficient?
Yeah. It's the exponent. Coefficient. Yeah.
No, I don't think you need to multiply moles by the coefficient. If you have a subscript, you have to multiply the moles by it.
Okay.
But we only use the coefficients when we're doing the stoichiometry going from one thing to another. There's not a lot of problems that have parts like this, and especially that last part, part D, where you've got to find the concentration of all ions. But there are a few. And I don't remember, the 61 may have been even assigned. And if that's the case, well, you just try not to look back at this and see if you can go through and do the whole thing yourself. All right. Now, I'd like to invite you, I'm just leaving this whole thing open, A, B, C. See if you can work through this yourself. And please feel free to talk to others and see what you can do. Are we still recording? Did you see it?
Yeah.
We're still going. Okay, good. Nope. You want me to close the door for that, or is that okay? I got it.
All right.
Absolutely work together if you want to. This problem stinks.